Hello and welcome to Meduhub. I am Neha Gupta from your chemistry faculty, and this is the second part of the video about aldehydes and ketones. In part 1 of aldehydes and ketones, we spoke about their structure, their nomenclature and their methods of preparation. In today's video, we are going to be talking about the chemical reactions of aldehydes and ketones. So aldehydes and ketones undergo some common reactions and some reactions which are specific to them. So I have divided these into three categories. Obviously, the first one is the reactions given by both aldehydes and ketones. The second one are the reactions specific to aldehydes, and the third would be the reactions which are given by ketones only. Now, the reactions which are common to aldehydes and ketones, common reactions, there are four common reactions. The first one is nucleophilic addition reaction. We have already talked about the mechanism of nucleophilic addition reactions and how is it that aldehydes are more reactive than ketones. The second is nucleophilic addition is the first one. The second is reduction reaction. Then there are reactions which are due to the acidity of alpha hydrogen. And the fourth category, which is valid for aromatic aldehydes and ketones, is electrophilic substitution. So these are the four types of reactions which are common. We'll start with the first one, that is nucleophilic addition. Nucleophilic addition. So when we talk about a carbonyl group, this carbon is an electrophilic center. Why? Because oxygen has a strong minus I effect because it is electronegative. So this has a slight positive charge, this has a slight negative charge. This is the reason why a nucleophile, which is an electron-rich species, would want to attack a carbonyl carbon. Now, aldehydes are more reactive than ketones because of two reasons which we've already talked about. One is the steric reason and other is the inductive effect reason. So now, since in aldehydes, the carbonyl carbon is attached to one R group and the other group is a hydrogen atom. So when the hybridization of this carbonyl carbon changes from sp2 to sp3, it becomes tetrahedral, and because of that, in case of ketones where there are two R groups, there is more steric hindrance, whereas in aldehydes it is less. That is one of the reasons. Other one is the electronic reason or the inductive effect. So here, if there are two R groups, the plus I effect of both the R groups will reduce the electrophilicity of this carbon. If one of this R group is a hydrogen, the electrophilicity would be reduced to a less level. That is why, due to the inductive effect of the R groups, aldehydes are more reactive than ketones. Now, what happens when a nucleophile attacks the carbonyl carbon? We get a tetrahedral intermediate like this, which in the presence of acid gives us this product, which is the addition product. Now this product here has four groups attached, so the hybridization of carbon changes from sp2 to sp3. Nucleophilic addition reactions are acid catalyzed. We already know that aldehydes are more reactive, but if we compare an aromatic aldehyde like benzaldehyde with, say, CH3, CH2, CHO, that is propanol, which out of the two would you think is more reactive? So if we have to compare the reactivity, we have to look at how electrophilic the carbonyl carbon is. So this is a normal aliphatic aldehyde and the carbonyl group is flanked by an R group, and this is sufficiently electrophilic for the reaction to have a good reactivity. But in the case of benzaldehyde, what happens? This double bond is in conjugation with this one here and oxygen is electronegative. So resonance takes place. Because of which, look at the next structure here, we will get a positive charge here, double bond here, negative charge here and H. Now this will move in the ring and the next structure would be with a positive charge on this carbon, and this will stay as it is, and so on. So because of the resonance of this pair of electrons with the ring, the positive charge is delocalized over the entire benzene ring. This leads to reduction of electrophilicity of this carbon. So the positive charge on this carbon is spread over the ring rather than being concentrated on this carbon like it is in propanol. Because of this reason, if you compare these two, this one will be more reactive towards nucleophilic addition reactions. Alright, now let us take specific examples. So the 4 reactions of aldehydes and ketones are: one is addition of hydrogen cyanide, second is addition of sodium hydrogen sulfide, third is addition of Grignard reagents, and the fourth is addition of ammonia and its derivatives. We'll do all of them one by one. So under nucleophilic addition, the first reaction is addition of HCN. Now hydrogen cyanide is a weak acid and it ionizes partially. So to produce cyanide ions, we need a basic medium. Hence this reaction is catalyzed by a base. Because of the presence of this base, we get Cn minus plus H2O. Now these cyanide ions are strongly nucleophilic. This now attacks the carbonyl carbon. So if we have this here, plus Cn minus, this will attack here, come here, and we will get this intermediate O minus and Cn. This in the presence of acid now will give us CH3, this here, OH and Cn. This product is a cyanohydrin. So aldehydes and ketones add on HCN to give a cyanohydrin. Now all aldehydes form cyanohydrins, but only acetone, butanone, pentane 3-one and pinacolone, that is this molecule. Only these 4 ketones give this addition reaction with HCN, or only these 4 ketones from cyanohydrins. Otherwise all aldehydes form cyanohydrins. Next reaction in nucleophilic addition is addition of sodium hydrogen sulfide. NaHSO3. This is the carbonyl compound. We have acetone here. This will add on NaHSO3 to form a bisulfite compound. Which is this. This bisulfite is upon reaction with dilute acid or alkali regenerates the carbonyl compound. And for such a reaction, the equilibrium majorly is towards the right side for aldehydes, because aldehydes are more reactive, and for ketones, the equilibrium is more towards the left side. Next reaction is addition of Grignard reagents. So we have a carbonyl group here. This reacts with R MgX. Here a negative charge here, partial negative charge here, partial positive here. When a Grignard reagent reacts with a carbonyl compound, we get this intermediate which decomposes with acid to give us an alcohol. So with Grignard reagent, an alcohol is the product. So if we have formaldehyde, we get a 1 degree alcohol. All other aldehydes on reaction with a Grignard reagent give us a secondary alcohol, and ketones with Grignard reagents give us a tertiary alcohol. Let us take some examples. So this is formaldehyde. This will react with RMgX to give this alcohol. This is ethanol, 1 degree alcohol. If we have ethanol, this will react with RMgX acid. This is a 2 degree alcohol. And if we have acetone, with acid, we will get a tertiary alcohol. Here, 1 degree, 2 degree and 3 degree. So this is it for the reaction of aldehydes and ketones with Grignard reagents. Next very important category is addition of ammonia and its derivatives. NH3 or its derivatives, which can be written as NH2Z. So in this case, this Z can be an alkyl group, an aryl group. It can be OH, it can be NH2, it can be NHC6H5, it can also be NHCO, NH2, or it can be a derivative of this, NHC6H5, NO2 whole twice. What happens when across a carbonyl compound ammonia or its derivative gets added? A molecule of water is eliminated here. So this oxygen and 2 hydrogen from here are eliminated, and we get carbon double bond nitrogen Z here. So what has happened? This oxygen and these 2 hydrogens leave, and this carbon now forms a double bond with this nitrogen, and the Z group here stays as it is. So when an aldehyde or a ketone reacts with ammonia, we can write it like this, NH2H. This will react together and a water molecule would be lost. So these 2 hydrogens, this oxygen will go and we will form an imine. Double bond NH. This is an imine. So ammonia on reaction with a carbonyl compound gives imine. Now let us see what happens if we use derivatives of ammonia. So if we have an alkyl group, aryl group, OH, NH2 and so on. We have a carbonyl compound. This reacts with NH2R. That is a primary amine. That means an alkyl group is attached to NH2 here. These two hydrogens, this oxygen will go away and we will get a substituted imine, double bond nitrogen R. This is a substituted imine or a Schiff's base, right? So the reaction of a carbonyl compound with an amine gives a substituted imine. Now if we have an aryl group attached, for that let us take this one. We have benzaldehyde reacting with aniline. So aniline here is NH2Z. Z is an aryl group. So NH2 attached to an aryl group here. This will lose a water molecule and we will get this as the product. This has carbon, double bond. This oxygen, these two hydrogens will go away and another benzene ring here. So this is the product when Z is an aryl group. Here an alkyl group was there, right? Next, if we have an OH group, that means reaction of a carbonyl compound with hydroxylamine. That would be NH2 and to it Z is OH, NH2OH, that is hydroxylamine. A reaction of a carbonyl compound with hydroxylamine would give us an oxime. So what will happen again? These two hydrogens, this oxygen will leave as water. This is the carbonyl carbon. This will now be doubly bonded to the nitrogen and the Z group will stay as it is. So this is an oxime. Oximes have a characteristic color depending on the carbonyl compound that we have used. So this reaction can also be used to determine which aldehyde or ketone is there. So it is used for the identification of aldehydes and ketones. If we have hydrazine, in the case of hydrazine, this is the carbonyl compound. NH2 is attached to NH2. This is hydrazine. Now NH2Z, this part is the Z part. What will happen now? Upon reaction, this oxygen, these two hydrogens will go and we will get this carbon doubly bonded to the nitrogen and NH2 here. This is called a hydrazone. Hydrazone. Next is if the Z is NHCO, NH2. This is semi-carbazide. So if a carbonyl compound reacts with a semi-carbazide, that would be, I'll write it with a different color for you to understand which hydrogen is which, which nitrogen is which. Alright. So now a reaction will take place, water will be lost, this carbonyl carbon is here, doubly bonded to this nitrogen and this nitrogen is now attached to this group. This is Z. This product is called a semi-carbazone. Right? The Z can also be phenylhydrazine. That is NH attached to a benzene ring. So if we have a carbonyl compound reacting with phenylhydrazine, NH2, this one, phenyl hydrazine. Upon losing water, it forms phenyl hydrazone. So, this oxygen again and these two hydrogens will go. This carbon will be doubly bonded to the nitrogen. And this group will come as it is. This is a phenyl hydrazone. If a derivative of phenyl hydrazone is there, that is called 2,4-DNP derivative. That is 2,4-dinitrophenylhydrazine. This is the carbonyl compound. This reacts with a derivative, that is NH2. The derivative is 2,4-DNP. So NH attached to a benzene ring. And at the 2 and the 4 position, we have NO2 groups. This is 2,4-dinitrophenylhydrazine. This will give, upon losing water, again these two hydrogens, this oxygen, and this group will come as it is, NH. This is 2,4-dinitrophenylhydrazone or a 2,4-DNP derivative. Just like oximes, 2,4-DNP derivatives are also solids of striking colors. So yellow, red, orange, these can also be used for characterization of the aldehyde or the ketone that we are using. So these are all the reactions of aldehydes or ketones with ammonia and its derivatives. The next reaction is reduction reaction. Reduction reactions are also given by both aldehydes and ketones. The first one is reduction, that is catalytic reduction with nickel, palladium or platinum catalyst. So this would be addition of hydrogen. So we have an aldehyde here. In the presence of any of these catalysts, to give us an alcohol. So an aldehyde gives us a primary alcohol, and if we catalytically reduce a ketone, addition of hydrogen, the presence of a catalyst, we get a secondary alcohol. Now, catalytic hydrogenation is also used for the reduction of double bonds. So, if we have a compound which has a double bond as well as a carbonyl group, both of these would be reduced to give us an aliphatic, totally saturated alcohol. Apart from this, another way to reduce is using lithium aluminium hydride or sodium borohydride. So similar to this, an aldehyde when reduced with lithium aluminium hydride gives us a 1 degree alcohol, and a ketone gives us a 2 degree alcohol. The third method of reduction is called Clemmensen reduction. What happens in Clemmensen reduction? We have a carbonyl compound when it reacts with amalgamated zinc. So zinc with an amalgam with mercury, the presence of HCl, this carbonyl group CH2 gets reduced to a CH2 group. That is, we get a hydrocarbon here plus water. So for example, if we have a ketone like acetone, the presence of zinc, mercury and HCl, we will get propane and water as the product here. This is Clemmensen reduction. The fourth method of reduction is Wolff-Kishner reduction. In Wolff-Kishner reduction, a semi-carbazone or a hydrazone, they reduce in the presence of KOH in ethylene glycol. And the entire group attached to the carbonyl carbon is reduced and we get a CH2 group instead of the carbonyl carbon that was initially there. So if we have a carbonyl compound like this can add on hydrazine and we will get a hydrazone here with a loss of water molecule. This hydrazone, or it can react with the semi-carbazide with a loss of water molecule to give a semi-carbazone. Semi-carbazone. Both of these can be reduced with KOH in ethylene glycol as the solvent. So this and this part would be completely reduced to give us a hydrocarbon. Plus nitrogen would be released. So this is Wolff-Kishner reduction, in which a hydrazone or a semi-carbazone reduces to a hydrocarbon. This is it for the reduction reactions. Next reaction is due to the acidity of alpha hydrogen. So the third category of reactions given by both aldehydes and ketones are the reactions due to acidity of alpha hydrogen. Now, this is the carbonyl group. The carbon to which it is directly attached is the alpha carbon. This hydrogen here is the alpha hydrogen. Now, what is it that makes this alpha hydrogen acidic? What is it that makes this CH bond so easy to break? The reason lies in the electronegativity of oxygen. So first, oxygen has a minus I effect because of its electronegativity. So this entire carbonyl group is a minus I group, because of which it pulls away the electron density between these two towards itself. Consequently, the pair of electrons between this carbon and hydrogen, that is the electrons in this covalent bond, are also pulled towards this carbon. So now if in this bond the shared pair of electron is more towards carbon, this hydrogen can be easily removed by a base. This movement of electrons towards this carbon facilitates the removal of this hydrogen as a proton. So one is this reason, because of the minus I effect of the carbonyl group. The other reason is, if you look at the conjugate base, this is the alpha hydrogen, this is the carbonyl group. Now, if we have a base, this will take away this alpha hydrogen. These two electrons will move to this carbon. Hydrogen will leave as proton. and we will get a conjugate base here. This is the conjugate base of this acid, which is an anion, a carbon ion. This carbon ion is resonance stabilized because this negative charge or this pair of electrons can move here and this one moves here. So we can draw another resonating structure for it, which goes like this. Because of the resonance stability of the carbon ion over this acid, this hydrogen, the removal of this hydrogen as a proton is favorable because the conjugate base is more stable than the parent acid. So because of these two reasons, the alpha hydrogen is acidic in aldehydes and ketones. Now what reactions do aldehydes and ketones undergo because of the presence of this alpha hydrogen? That reaction is a very important reaction which is called aldol condensation. In aldol condensation, two molecules of a carbonyl compound, be it aldehyde or ketone, combine together with or without elimination of a water molecule. So when two molecules of the same aldehyde combine together, they give a beta hydroxy carbonyl compound or an aldehyde, which is called aldol. Or when two molecules of ketones combine together, gives beta hydroxy ketone, which is called a ketol. Both aldol and ketols, when heated, lose a water molecule and they form alpha beta unsaturated aldehydes or ketones. So this is aldol condensation. First two molecules of say an aldehyde combine together, they will form an aldol. This aldol upon heating can lose a water molecule and form the alpha beta unsaturated aldehyde. Now what is the mechanism of aldol condensation? We look at it using an example. So let us carry out the aldol condensation of ethanol. So in the first step, what will happen? This is ethanol. These are the alpha hydrogens. This is the carbonyl carbon. These reactions are base catalyzed because the base can take away the alpha hydrogen. So in the presence of a base, this base will take away this hydrogen and a carb anion will be formed. So first step is the formation of a carb anion. Now this carbon will have a negative charge. This carbonyl group is here, plus H plus. Now in the second step, one molecule of ethanol will add on to this carb anion here. This is the carb anion and this is the molecule of ethanol. Because this is an electrophilic center, this negative charge will attack here. This electron pair will move to the oxygen atom and we will get CH2 COH to this carbon. Now this carbon is getting added, O minus and a CH3. This intermediate formed in the presence of acid will give us this CH2 group here attached to a CH. This is attached to a CH3. This CH has O minus, so in presence of proton it will give OH and this is attached to a carbonyl group here. So you see this is alpha carbon, this is beta carbon. So this will be the beta hydroxyaldehyde now. If you have to name it, you will number the carbons 1, 2, 3, 4. So this will be beta hydroxy butanol. This beta hydroxybutanol, upon heating, if we heat it, it will lose an alpha hydrogen from here. And OH from here. That means a molecule of water would be removed from this aldol here to give us CH3, CH. Now a double bond is going to get formed here. Now this is the alpha carbon and this is the carbonyl group. So this would be the alpha beta unsaturated aldehyde. Now the OH group is flanked by hydrogens on both the sides. But why is it that only the alpha hydrogen gets lost on heating and not the hydrogen on this gamma carbon here, not the gamma hydrogen? That is because if you look at an alpha beta unsaturated compound, you will see that it is resonance stabilized. Because this double bond will be in conjugation here with this carbon oxygen double bond. But if you have a beta gamma unsaturated compound like this, this beta gamma unsaturated compound has no resonance stability because this is not in conjugation with this double bond. Hence, upon heating, only the alpha hydrogen is lost and we get this alpha beta unsaturated aldehyde. So this is the mechanism. We'll take one more example to understand aldol condensation. So let's say we have two molecules of propanol condensing together. In the presence of a base like barium hydroxide now, one molecule will form the carbon ion. Let me write it here. This carbon is the carbonyl carbon. This CH3 group is as it is. The other CH3 group loses a hydrogen. This one forms a carbon ion here. This carbon ion is attacked by attacks on this carbonyl carbon, the carbonyl carbon of the other molecule. So this carbon will get attached to this one here, this. Both the CH3 groups are as it is. And in the presence of acid, this will become OH. So this is the product of aldol condensation between two molecules of acetone. So you see, this is the alpha carbon, this is the beta carbon, this is beta hydroxy ketone. Now this beta hydroxy ketone on heating will lose a molecule of water to give this hydrogen will get lost, this OH group will be removed and we will get CH double bond C, CH3, CH3. So the alpha beta unsaturated product. This is self-aldol condensation or simple aldol products. What happens if we use two different molecules of aldehyde or two different molecules of ketone or one molecule of ketone and one molecule of aldehyde? So when such a scenario takes place, it is called cross-aldol condensation. So cross-aldol condensation is also aldol condensation. It takes place between molecules of aldehydes and ketones which have an alpha hydrogen. Okay. So if we have two molecules of ethanol, we have ethanol reacting with, let's say, propanol. So this is a case where we have two different aldehydes. Now both the aldehydes have alpha hydrogens. This will give us 4 different products. How will that happen? The first product would be a simple aldol condensation product between two ethanol, right? So aldol condensation between two molecules of ethanol. This would give us, this is the carbonyl carbon. The alpha hydrogen was lost from here. So this formed a carbon ion. This carbon ion attacked another molecule of ethanol at this carbonyl carbon. To give us this hydroxy compound. Now this will lose a molecule of water and give us this will be the simple aldol product between two molecules of ethanol. Now two molecules of propanol can also have a simple aldol product. Second would be aldol product of two molecules of propanol. One molecule of propanol will lose an alpha hydrogen. So we will have, this is the carbonyl carbon. This will lose an alpha hydrogen, CH3 is attached here. This will attack the carbonyl carbon of another molecule of propanol here. This is the beta hydroxy aldehyde. This will lose water on heating. So this and this will get low, and we will get double bond CH, CH2, CH3 here. So this is a simple aldol product of aldol condensation between two molecules of propanol. The third product would be a cross aldol product between one molecule of ethanol and one molecule of propanol. Here two scenarios can exist. One in which ethanol forms a carbon ion and that carbon ion attacks on propanol, on the carbonyl carbon of propanol. The other scenario will be when propanol loses an alpha hydrogen, forms a carbon ion, and this carbon ion now attacks on the carbonyl carbon of ethanol. So in the first case, let's say ethanol forms the carbon ion. This would be like this, attached to the carbonyl carbon. It formed a carbon ion, CH2. I am not writing the negative charge because this will get attached to this carbonyl carbon. This carbon ion now attacks the carbonyl carbon here. This O becomes OH now. And rest is CH2, CH3. This is the product. This can lose a water molecule. And it will form CHO, CH double bond CH, CH2, CH3. So this is a result of a cross aldol condensation between ethanol and propanol where ethanol lost the alpha hydrogen. Similarly, the fourth product would be when propanol forms the carbon ion. Here CH3, CH, and this is the carbonyl group. This alpha hydrogen is lost. Now this CH here will attack the carbonyl carbon of ethanol. And we will get this beta hydroxy alcohol, aldehyde. This beta hydroxy aldehyde upon heating will lose a water molecule and we will form this product CH3 CHO, here double bond CH3. So these 4 products formed here are the possibilities when 2 different molecules of aldehydes react. Okay, 2 products will be simple aldol products, 2 products will be cross aldol products. Now if we have these 2 molecules here, acetone reacting with ethanol. So this would mean a ketone is reacting with an aldehyde. In such a scenario, when a ketone reacts with an aldehyde, one, we can easily get the simple aldol products of acetone combining with acetone. The other product would be a simple aldol product of ethanol combining with ethanol. And the third product would be a cross aldol product between acetone and ethanol. In such a scenario, only the alpha hydrogen of the ketone is involved in cross aldol formation. So the first product, understand again, will be a simple aldol product between acetone and acetone. Second can be a simple aldol product between ethanol and ethanol. Now when these 2 are combining or condensing together, alpha hydrogen only from acetone will be lost, and the cross aldol product that you will get here in the presence of a base would be this. This is acetone. It lost an alpha hydrogen from here, so CH2. This combined with this carbonyl carbon here, and this is the beta hydroxy ketone that we get. This is the cross aldol product. This is apart from the simple aldol products between acetone and ethanol. The third product which will be formed will be this, which will lose a water molecule to finally give us this product. This will be the cross aldol product. It is formed around 25%. So when a ketone and an aldehyde react, we get, if both of them have alpha hydrogens, we get 3 products. If we have an aromatic aldehyde, how does it make a difference? So we have benzaldehyde reacting with, let's say, acetophenone. Benzaldehyde does not have an alpha hydrogen because the alpha carbon is this carbon here. Alpha carbon is attached to 3 other carbons and there is a double bond between this carbon and this carbon. So benzaldehyde has no alpha hydrogen. So this simplifies our product because only this molecule has an alpha hydrogen here. So the alpha hydrogen would be lost from here. We can draw it like this, the structure. This is the carbonyl carbon. Instead of CH3 now we will have CH2. 1 hydrogen lost from here. This carbon will attack this carbonyl carbon here. This is this carbon. The carbon here is this. This will get attached to OH now. And further it is attached to a benzene ring. This is the product. This will lose a water molecule on heating to give this as the product. Alright. So in such a scenario, when only one molecule has an alpha hydrogen, the products become very simple and only this one here is going to lose the alpha hydrogen and condense with a molecule of benzaldehyde. The aldol condensation or cross aldol condensation of aromatic aldehydes with aliphatic aldehydes or aliphatic ketones is called Claisen condensation. The mechanism and the products are the same as aldol condensation. One interesting reaction is between benzaldehyde and ethanol. This is benzaldehyde, this is ethanol. Now, benzaldehyde does not have an alpha hydrogen. Ethanol has an alpha hydrogen. This is ethanol. Here, one hydrogen will be lost, we'll get CH2. This carbon will attack this carbonyl carbon here. So, this oxygen will now become OH group and the benzene ring is here. This, when heated, will lose water and we can draw the product. This OH and one of this hydrogen will be removed. So we will have CH, double bond, CH and CHO. So this is cinnamaldehyde. This is the compound that is present in cinnamon. So it can be prepared by a reaction between, a Claisen condensation between benzaldehyde and ethanol. So this is it for the reaction due to alpha hydrogen. So aldehydes and ketones which have an alpha hydrogen undergo condensation reactions. If two molecules of the same compound are condensing, it is called aldol condensation. If two different molecules are condensing together, it is called cross aldol condensation. The last reaction, which is common to aldehydes and ketones, the fourth one is electrophilic substitution. We have already talked about electrophilic substitution in aromatic compounds. So this is valid for aromatic aldehydes or ketones. If you look at the carbonyl group here attached to a benzene ring, you will see that upon drawing the resonance structure, the ortho position here gets a positive charge. If we further draw the resonating structures, these two electrons will move here to form a bond, and the next structure here has a positive charge on the para position. And in the next, again the ortho position gets a positive charge. So you see that the ortho and the para positions get a positive charge, which makes the meta position relatively more electron rich compared to the ortho and para. So it is not that the meta position is getting extra electrons through resonance. It is not. But compared to the ortho and para positions which are getting a positive charge, the meta position is now relatively more electron rich. This implies that because of the carbonyl group present on the benzene ring and its minus R effect, the carbonyl group here is meta-directing. And obviously due to the minus R and the minus I effect of COO group, it is deactivating also. So it is meta-directing as well as deactivating towards electrophilic substitution reactions. What are the substitution reactions that can take place? We will discuss 2 or 3. One would be nitration. So if we have benzaldehyde, the presence of HNO3 and H2SO4, we will get this product. So nitro group will get attached to the meta position. This would be meta nitro benzaldehyde. Similarly, if we have acetophenone combining with HNO3 and H2SO4, we will get meta-nitroacetophenone. If we have to carry out bromination, benzaldehyde reacting with bromine in the presence of excess of AlCl3 gives us meta-bromobenzaldehyde. And if we carry out sulfonation, say we have acetophenone, it combines oleum or fuming sulfuric acid, H2SO4, SO3, to give the SO3H group at the meta position again. Here, you should know that acetophenone is so deactivating that it does not undergo Friedel-Crafts reaction. Right? So this is it for the common reactions of aldehydes and ketones. There were 4 reactions. Now we will move on to the reactions given by aldehydes only. First reaction is reaction with alcohols to form hemiacetal, which eventually gives us an acetal. Second is the oxidation reaction of aldehydes. Oxidation reaction of aldehydes are very important because they help us distinguish aldehydes from ketones. We'll see how. There are 2 oxidation reactions, Tollens test and Felling's test. These are not given by ketones but only by aldehydes. The third reaction is Cannizzaro reaction. This is a reaction given by aldehydes which do not have an alpha hydrogen. So it is of more significance for aromatic aldehydes. We'll go through them one by one. So this is reactions given by aldehydes only. One is reaction with alcohols. So we have an aldehyde. This adds on a molecule of alcohol. In the presence of acid to first give a hemiacetal. So we will get this. R dash to distinguish. This is a hemiacetal. This hemiacetal readily combines with another molecule of alcohol, the presence of acid, to give an acetal. So OR dash, OR dash. This is an acetal. So basically acetals are diether compounds of the unstable 1,1-dihydroxy alcohols. So instead of OR, if you imagine OH, the hydroxyl group is attached to the same carbon. So there are geminal dihydroxy compounds. These are diethers of those compounds. This is the nucleophilic addition reaction of aldehydes with alcohol. Now, these acetals, when treated with acid, give back the aldehyde that we started with. But they do not react with bases. So it is a very good method of protecting this group so that we can use this reaction for the purification of aldehydes. Next reaction of aldehyde is the oxidation reaction. Oxidation reaction. Aldehydes readily undergo oxidation. So RCHO upon oxidation gives RCOOH, that is a carboxylic acid. The carboxylic acid formed has the same number of carbon atoms as the parent aldehyde, and all good oxidizing agents like HNO3, KMNO4, K2Cr2O7 oxidize aldehyde to ketones or to carboxylic acids. What is special about aldehydes is that even mild oxidizing agents like Tollens reagent and Fehling solution, these mild oxidizing agents also oxidize aldehydes to carboxylic acids or their salts. Now, this is important because this reaction is not given by ketones. So, the Tollens test or the Fehling's test are two reactions which are not given by ketones because ketones are not easily oxidized. Hence, these two reactions can be used to distinguish between aldehydes and ketones. And if you're given two samples of carbonyl compounds, one an aldehyde, other a ketone, by carrying out either of these reactions, you can find out which one of them is an aldehyde, which is the ketone. So, what happens in a Tollens test? We have an aldehyde which reacts with freshly prepared ammonical silver nitrate solution. Ammonical silver nitrate AgNH3 whole twice plus an OH minus. Freshly prepared ammonical silver nitrate oxidizes the aldehyde, the Tollens reagent, to the corresponding carboxylate ion, and we get NH3, H2O and silver. So basically in this reaction, when aldehyde gets oxidized by Tollens reagent, silver is precipitated, and in the test tube you can see a silver mirror-like coating forming at the sides and at the top. So this is the reaction. Visually you can immediately find out if the Tollens reagent has oxidized the given carbonyl compound or not, because if the reaction has taken place, a silver mirror would be formed. This is the Tollens test. Next test is the Fehling's test. It is important to know that benzaldehyde also gives the Tollens test, benzaldehyde. The next test is the Fehling's test. Fehling's solution also oxidizes an aldehyde to the corresponding carboxylate ion, and it gives cuprous oxide, Cu2O, which is reddish brown in color. So when an aldehyde is treated with Fehling's solution, we get a red-brown precipitate and a carboxylate ion of the corresponding aldehyde is formed. Through this, we get to know that whatever compound we were starting with was an aldehyde. Again, Fehling's test is not given by ketones, And Felling's test is also not given by aromatic aldehydes. So Felling solution is made up of Felling solution A and Felling solution B. Felling solution A is an aqueous solution of copper sulfate CuSO4, which is blue in color. Felling solution B is sodium potassium tartrate, which is also called Rochelle salt. When you mix both of them in equal amounts, that is freshly prepared Felling solution, it reacts with aldehydes. So we have RCHO reacting with Cu2 plus, and this is an alkaline solution. It gives us RCOO minus plus Cu2O. This precipitates and gives a reddish brown PPT. So these are the two tests of oxidation reactions of aldehydes not given by ketones. The next reaction is a Cannizzaro reaction. Now Cannizzaro reaction is also only given by aldehydes. It is important to know that the Cannizzaro reaction is given by aldehydes which do not have an alpha hydrogen. Aldol condensation is given by aldehydes which have an alpha hydrogen. Cannizzaro's reaction is given by aldehydes which do not have an alpha hydrogen. So, if we have formaldehyde, here, this will undergo Cannizzaro reaction. Cannizzaro reaction is a reaction which takes place in the presence of a 50% solution of KOH or NaOH in alcohol or in water. So this is concentrated NaOH or KOH. In this reaction, the molecule of aldehyde undergoes self-oxidation and self-reduction. So what happens? One molecule gets reduced to an alcohol, the other molecule gets oxidized to the carboxylate ion or the carboxylic acid salt. So this is a disproportionation reaction. Where the same molecule is undergoing oxidation as well as reduction. So this in the presence of concentrated NaOH would give CH3OH as the alcohol. This is the reduction product, and we will get which is the oxidation product here. So this is the sodium salt of the carboxylic acid, and this is the alcohol. This is more appropriate for aromatic aldehydes. Why? Because apart from formaldehyde, all the other aliphatic aldehydes will have an alpha hydrogen. So all aromatic aldehydes do not have an alpha hydrogen. So we can write down this reaction for benzaldehyde as well. CHO conc NaOH. No alpha hydrogen here. One molecule will be reduced to alcohol, benzyl alcohol, and the other molecule will give us sodium benzoate, COO-Na. So this is the Cannizzaro reaction where self-oxidation and self-reduction of an aldehyde takes place. The third category of reactions now will be the reactions which are given by ketones only. Reactions given by ketones only. we talk about oxidation here, ketones are very difficult to oxidize. They are not easily oxidized to carboxylic acids. So you need drastic conditions like very strong oxidizing agents and elevated temperatures. When such conditions are used, if we have this ketone, this will break down into smaller carboxylic acids. So the difference between aldehydes and ketones is when you forcefully oxidize a ketone, it will not give a carboxylic acid containing the same number of carbons as the ketone, but we will get smaller carboxylic acids or carboxylic acids containing less number of carbons. So for example, if this is the ketone, arbitrarily, this is carbon A, carbon B and carbon C. On drastic oxidation, either the bond between carbon A and B breaks from here. So this part will get oxidized to a carboxylic acid. We will get RCOOH, and this part will get oxidized. So we will get R-CH2COOH, or the bond between carbon B and C can break. This one here. So if this bond breaks, this entire part will get oxidized first. So we will have RCH2COOH plus this part, that would be R-COOH. So we are getting a mixture of carboxylic acids all having different number of carbons. So we get 4 products here. So this is oxidation of ketones. It is very much different from oxidation of aldehydes, and we will always get a mixture of carboxylic acids containing lesser number of carbons. It is now obvious that ketones do not give the Tollens test or the Felling's test. But one very important reaction of oxidation reaction of ketones is called the haloform reaction. Haloform reaction is used for the identification of methyl ketones. Methyl ketones would mean ketones which have an acetyl group, that is COCH3 here. This can be attached to any other R group here. This acetyl group makes a ketone a methyl ketone because on one side of the carbonyl carbon we have CH3. Now, this reaction is also given by ethanol. Why? Because if you look at ethanol, it also contains the acetyl group here, CH3CO. This is the only aldehyde which gives the haloform reaction. And thirdly, if we have an alcohol like this, with this group present, this also gives the haloform test because the reagent used for a haloform reaction, sodium hypohalite NaOX, is an oxidizing agent. So this group here will first get oxidized to an acetyl group, and once it has become an acetyl group, it will give the haloform reaction. So haloform test can be used to determine if a given compound has an acetyl group. So it can be used for detection of this as well as this. All methyl ketones, this kind of alcohol, and this ethanol molecule, only aldehyde. So what happens in a haloform reaction? NaOX would mean we have iodine or bromine or chlorine in an NaOH solution. This gives sodium hypohalite. So if we have a methyl ketone, this, let's say, reacts with sodium hypoiodide NaOI. Hypoiodide. This part will get oxidized to the corresponding carboxylic acid ion or COO minus, and we will get haloform or iodoform here as the precipitate, CHI3. Iodoform will precipitate, which is pale yellow in color. So if we get a precipitate that is iodoform or any other haloform precipitates, we get to know that the ketone that we started with was a methyl ketone. The carboxylate ion we get here contains one carbon less than the parent ketone, because the methyl group here reacts with sodium hypohalite, giving us iodoform here. So this is a very important reaction called the iodoform reaction if we use sodium hypohalite or hypoiodite, or it's called the haloform reaction. So this is an important reaction of ketones, oxidation reaction, that is the only one given by ketones. Alright. Now if you have a ketone which has a double bond present in it, like this one here, so this double bond is not affected by any OX. So when this forms a carboxylate ion here, this double bond remains as it is and we still get iodoform, or in this case chloroform. The last reaction that is given by ketones and not given by aldehydes is reaction with ethylene glycol. Ethylene glycol is this. So ketones, like aldehydes, do not add on a molecule of alcohol to give us hemiacetals or acetals. But in the presence of an acid, a ketone adds on a molecule of ethylene glycol to give ketones, a cyclic ketone. This carbonyl carbon now attaches to oxygen here, CH2, this CH2 here, oxygen and this. This is a cyclic ketone. So this is the difference between aldehydes and ketones. Aldehydes they react with molecules of alcohol to give acetals, but ketones do not react with alcohols, they only react with ethylene glycol, here vicinal hydroxyl compound, to give a cyclic ketone here. Right? Ethylene glycol ketone. This is it. So these were the three categories of reaction, one given by both aldehydes and ketones, one given by only aldehydes, and this one given only by ketones. This concludes our two-part series of aldehydes and ketones, part 1 with the preparation nomenclature, part 2 with all the chemical reactions. Thank you so much for watching. I'll see you in the next video.